So today we'll finish talking about equivalence relations. So recall that an equivalence relation on a set is a reflexive, symmetric, and transitive relation. And a relation is just a subset of A cross A, as we've discussed in the past couple lectures. So the main concept we defined last time was equivalence class of an element A with respect to an equivalence relation, and that is a subset of A. It's the set of X in A that are related to that small a. So X in A such that X are A. Now, the most important property of equivalence classes that we proved last time, so we looked at it in the case of the integers mod n, that particular equivalence relation, and then we generalized it. The most important property is that two equivalence classes either don't overlap at all or they're exactly equal. So they can't have any non-trivial overlap. It's either completely disjoint or they're exactly equal to each other. And the equality of equivalence classes, so the equivalence class of A and the equivalence class of B are equal if and only if A and B are related by this equivalence relation. And a consequence of this is that every element of A is in exactly one equivalence class. Because any A is in its own equivalence class, so A is in the equivalence class generated by A, and if A were in some other equivalence class, say the equivalence class of B, then A is common to both of those equivalence classes, the equivalence class of A and the equivalence class of B, and since they overlap, they must overlap completely. They must be equal. So that's the overview of the proof that we talked about last time. So every element is in exactly one equivalence class, and so the picture that you get is something like the one below. Basically what happens is that your equivalence relation kind of breaks your set A up into different pieces, which is what we're going to call a partition. And so the picture is, as you see down here, if you have an equivalence relation, you look at all of the things that are related to each other. So like that grouping in red and blue and green and yellow there. And if you just bundle all those elements together, that gives you a subset of A. And since these subsets, they're the equivalence classes, every element of A is in exactly one equivalence class. So these subsets that you get, they have to cover the entire set A and they don't overlap with each other. And conversely, if you're given a bunch of subsets of A which cover all of A and which don't overlap, which is what we're going to call a partition, then that gives you an equivalence relation. You just define your equivalence relation to say that everything that's in one of those subsets in your partition, that those things are all related to each other, and we'll see that that is an equivalence relation. Okay, so the first thing is to define what we mean by a partition. So definition, a partition of a set A is a, so intuitively, what is this picture up here for partition telling us? It's a collection of subsets of A. So it's a subset of the power set of A, right? Collection of subsets, that would just be some things in the power set, right? So it's a subset, let's say Z, in the power set of A. And well, what property does this collection of subsets have? It has the property that, well, they cover all of A and they don't overlap at all, right? So one way we can say that is that every element of A is in one of these subsets of A, and that every element is in exactly one. Okay, so it's this subset of the power set with the property that every A, little a, in A is in one and only one element X in this Z. All right, so Z is an element of the a subset of the power set, so its elements are subsets, and so we can call that such a subset X, And so a partition has the property that every A is in one and only one capital X, which comes from this collection of subsets Z. Okay, so that's what a partition is. And now we're just going to state formally the proposition that is indicated in that picture above, that equivalence relations and partitions kind of just correspond to each other. So proposition, any equivalence relation R on A induces a partition, say Z sub R, and that's just a subset of the power set of A. And conversely, any partition Z, which is a subset of the power set, induces an equivalence relation. Let's say R sub Z. On A. Okay, so try to keep that picture in your mind, because we're basically just going to formalize that and write that down as the proof. So suppose first that R is an equivalence relation so we have an equivalence relation on A, and what we want to do is define a partition of our set A. So we have to define a bunch of subsets of our set A. And well, what's the picture say? The picture says when you have an equivalence relation, your subsets are just going to be the equivalence classes, right? All the things that are equivalent to each other. So we just define Z sub R to be the set of equivalence classes such that A is in A. Okay, so then we just have to check that this is a partition. So this is a partition of A. And the reason is, we've already said it. Every A is in exactly one equivalence class. As we've seen, every A in A is in exactly one equivalence class. Okay, that's it for that part of the proof. And conversely, let Z in the power set of A be a partition. And now we have to define an equivalence relation. So how are we going to define this set, which defines our relation? So R, it's going to be some X and Y in A cross A, such that, well, when are X and Y going to be related? So just go back to this picture here. So we're starting on the right with the partition. So our x and y are going to be related when there is a set in our partition. So that's a subset of A. So that subset of A coming from our partition. Our x and y are going to be related when there's one of those subsets which contains both of them. Okay, so we'll just say that x and y, they're in this relation set if there exists, so x and y in A cross A, such that there exists an x, capital X, in Z, such that little x is in capital X and y is in capital X. And maybe I'll write our logical and symbol. Okay, so that's it. So again, we just reference the picture and kind of write down what we see in the picture. So our things are going to be related when they're in the same element of this, when they're in the same subset that's in this, that's defined by this partition. Okay, so we need to check, that this is an equivalence relation. So one, we need to check reflexive, that the relation is reflexive. Okay, so we need to check that x is related to x. So for any x in A, since Z is a partition, remember the defining property of a partition is that for anything you take in A, that is in exactly one of the elements of the partition, right? Exactly one of those subsets that's in that partition. So in particular, there exists a subset of in the partition which X is in. Since Z is a partition, there exists an X in Z such that X is in Z. Such that little x is in that capital X. Thus, x is in X and X is in X is true. So X is related to X. Okay. Symmetry. Suppose that X is related to Y. Well, what that means is that there exists some X in our partition such that X and little Y are in big X. So then, thus there exists X in Z such that little x is in X and Y is in X. This is the same as Y is in X and X is in X. So Y is related to X by definition. That was an easy one. Just because basically P and Q is the same as Q and P, logically. And 3 is transitivity. Transitive. So suppose that X is related to Y and Y is related to X. Or sorry, Y is related to Z. Then by definition, then there exists a capital X and a capital Y in this capital Z, such that X is in X, Y is in X, and let me say, and y is in y, and z is in y. Okay, so now the key thing is we have to use a property of partition here, that an element can be in one and only one element of the partition. So since y is in x and y is in y, but z is a partition, it follows that actually capital X is equal to capital Y. So we have X is in X, Y is in X, and Z is in X. In particular, X is in X, and Z is in X. So X is related to Z. And that's the transitive property. And so that completes the proof. So all it really was is you have to define what you mean by partition precisely, and then you just take this intuitive picture you have and you just write that down in words. That's really all the proof comes down to. So logically speaking, equivalence relations and partitions, there's really no difference between them. You can toggle back and forth between them at will. Okay, so that's about the last thing to say formally about equivalence relations. I do want to go over another example of dealing with equivalence relations and equivalence classes. So here you have one last example. So I want to think about the rational numbers. And so rational numbers are fractions, right? So you have a over b, where a is an integer and b is a non-zero integer. So b non-zero is an integer. And one way to say this convenient shorthand is that b is in z star. So this z star, that is, the star is a common notation for removing zero from the set of numbers you're talking about. So this is the non-zero integers. And so you might in the future see R star or Q star or other things star. It says it means just remove zero from that set. Okay, so in the rational numbers, right, we know we have certain equalities. So for example, 1/2 is equal to 2/4, and it's also equal to 3/6, and it's also equal to 5/10, etc. And in general, so what's common among these things is that, so the general rule, in general, a over b, we consider these, right? So we have this one sort of notation for this rational number. It's this, you have this pair of integers, a and b, and we write a over b, but that's to be understood as equal to c over d, right? A potentially different pair when ad minus bc equals 0. Right? Again, we're assuming here that b and d, neither of those are equal to 0. Now, the way you're used to dealing with these these fractions, these rational numbers. A perfectly sensible and fine way to think about them is just sort of operationally, right? I mean, you know the rules for manipulating these things. You know when A over B is equal to C over D, and you sort of know what they mean. You know, like A over B means something like, well, you have a pie with cut into B pieces, and you're considering A of those pieces, right? A pieces of that size. So you have a relatively robust conceptual understanding and operational understanding of how to work with these rational numbers. But what mathematicians like to do is sort of worry about how to build up these rational numbers logically, right? So, I mean, this way of working with rational numbers you've been used to is a kind of I don't know, like folk knowledge or something. It's a working man's knowledge of the rational numbers, but the mathematicians want to make sure they're logically sound and build up from simpler things. So this is how mathematicians build up the rational numbers from the integers. So basically, when you have an A over B, right, that rational number, what the mathematician wants to do is formally think about that as a pair, A, B, right? And this pair is, so A is an integer and B is a non-zero integer. So this is in Z times Z star. But not really, right? Because we know that that A over B, that's going to be the same as, that could be the same as some other C over D, right? And C over D, that corresponds to a potentially different pair, right? If A and B are 1 and 2, right, and C and D are 2 and 4, these are two different pairs, right? So these things are equal here, but these things are not equal as elements of Z times Z star. But what we can do is, instead of talking about the pairs themselves, we can talk about their equivalence classes under some equivalence relation. Right? So what we're going to do is now think about these. So let me just get rid of this part here. So what we're going to do is think about these as equivalence classes of these pairs. All right? And the equivalence relation is exactly this thing here. Right, so our R, so we're going to define R to be, so the things we're considering are elements of Z cross Z star, right? And we have to consider equivalence classes of those. So we're going to be talking about one of those pairs being related to another pair, right? So our set, so our A set here is going to be Z cross Z star. All right, so our R is going to be pairs from A. Right, so what we're going to have is a pair where each element of the pair is a pair from Z cross Z star. So we have pairs A, B, and C, D, right, such that A, B, and C, D are both elements of Z cross Z star, and they're going to be equivalent, right? So they're in this relation set when AD minus BC equals 0. So AD minus BC equals 0. Okay. Right, so that is our set. Okay, so this is the formal way to think about fractions. If you believe in the integers, right, this formal construction is going to construct a model of the rational numbers, a perfectly logically sound model for the sort of ontology of the rational numbers. So we're building them up from something simpler. And it's basically just this idea of thinking about a fraction, right, that quotient of two integers as really an ordered pair, but since two integers as a fraction like that, you can have different pairs representing the same rational number. What we want to do is consider an equivalence class, right? So two different pairs could represent the same equivalence class as long as they're related, as we've seen. Okay, so the claim now is that R is an equivalence relation. So R above is an equivalence relation. On Z cross Z star. Proof. So we have to show that we have an equivalence relation, so there's three things to show, reflexive, symmetric, and transitive. So to show reflexive, we have to show that AB, the pair AB, is related to itself. And when that happens, well, in general, AB is related to CD if and only if AD minus BC equals 0. And so you can kind of visualize that as the first one in the first thing and the second one in the second thing, and then the second one in the first thing and the first one in the second thing. They pair up and you subtract them. So down here we have AB minus BA equals 0. And of course that's true. So it follows immediately that that AB is related to AB. The next thing we have to prove is symmetry. So to prove symmetry, we start with assuming that AB, some pair AB, is related to another pair CD. And then we want to show that CD is related to AB. So that is, we start by assuming that AD minus BC equals 0. And then let's write down what it means for CD to be related to AB. That means that C times B minus D times A is equal to 0. But that is just equivalent to the equation we already have, right? So CB minus DA equals 0. That's just the negative of the equation AD minus BC equals 0. And negative 0 equals 0, so those things are equivalent. And that second equation is just equivalent to CD being related to AB. And so we can just write that down nice and neat. So starting with AD minus BC equals 0, that's equivalent to CB minus DA equals 0. Just by multiplying that equation by -1 on both sides. And by definition, that means that CD is related to AB. The last thing to prove is transitivity. And so we start by supposing that one pair is related to a second, and then that second is related to a third. And we have to establish that the first and the third are related. So using A, B, C, D, and E, F, we are assuming that AD minus BC equals 0. And that CF minus DE equals 0. And what we're trying to get to is that AB is related to EF. So let's write down where we're trying to go here. That's the same as AF minus BE equals 0. And so we're trying to bridge the gap from the two equations we have to that equation. We see that in the equation we have the first equation we have an A, right? And we're looking for an AF. So what we're going to do is multiply that first equation by F on both sides, so we get an AF. And on the other hand, we're looking for where E is in our equation. So we see that E occurs in the second equation there, but without a B. So we're going to multiply both sides of that by B. And then we'll see where we can go from there. So multiplying the first equation by F and the second equation by B. Then we just write down the resulting equations. We have AFD minus BCF equals 0, and BCF minus DBE equals 0. And then what you can notice is that BCF occurs in both equations there. And so if we add them together, right, we can cancel those and get the AF and BE stuff all in one expression. And there's a common multiple of D, you might notice, in that first term of the first equation and the last term of the last equation. So we'll be able to factor that out, and that will get us what we need. So we add those two equations together. And we get AF minus BE times D equals 0. And from this we can conclude that AF minus BE equals 0 because D is not equal to 0. Because in these pairs, the second thing in the pair is never 0. And so D was the second thing in the pair CD. And AF minus BE equals 0 is equivalent to AB being related to EF. So that completes the proof of transitivity. All right, so this gives us a way of thinking about rational numbers that is a little more rigorous than you've probably seen before. So just again, basically the idea is that any pair, any rational number A over B, you can think about it as an equivalence class of the pair AB under this equivalence relation that we looked at here. Right? So you think of the fraction AB is the same as the fraction CD when AD minus BC equals 0. And that's just the same logical format as thinking of equivalence classes of two things being equal when they're related by a relation. Right? So our equivalence class of AB is equal to our equivalence class of CD when they're related. All right, the last topic we're going to look at is relations between sets. So far we've just looked at relations on a set, and we'll relativize that notion to talk about relations between sets. So it often occurs in mathematics that you have two sets that are related somehow, but the sets are different. See, relations not occurring just between elements in one set, but between elements in different sets. So the definition that we establish here is that a relation between sets, well, a relation between two sets is going to say that something in the set A is related to something in the set B. So those two things being related, they're they're going to be a distinguished pair in AB, in A cross B, A times B. So our relation is just going to be some subset of special pairs in A cross B. In other words, it's just a subset of A cross B. So a relation is going to be nothing more than a subset of A times B. So you see that a relation on a set A, we could rephrase that as a relation between a set and itself. And we write x, r, y, read x is related to y if x, y is in this relation set, where x is in A and y is in B. So I can look at an example. Probably the simplest class of example is where you take A to be a set, any set whatsoever, and B to be the power set of that set. And then there's a natural relation between things in those two sets, the relation of membership, whether a member of the set A is in the member of B that you're looking at, which is just a subset of A. So you have pairs of elements of A and subsets of A and X are related when A is in X. So it might be helpful to look at an example in a particular case. So we take A to be a set containing two elements. Then B is going to be the power set of that set. So we have the empty set, the set containing 1, the set containing 2, and the set containing 1 and 2. And we can represent our relation with a diagram like we were doing before, except now the diagram isn't in one set, it's just between the two sets. So we have arrows going from one thing in the set A to another thing in the set B. So since 1 is contained in the set 1 and the set 1, 2, then we have an arrow from 1 to both of those sets. And 2 is contained in the set that just contains 2 and the set containing 1 and 2. So there's going to be 2 arrows from 2 to each of those sets. And that's the diagram of our relation. Another general example is if we take the natural numbers to be our set A, we let C be any set, then we can take our B to be the power set of C. And the relation is just going to be that N and X in B are related when X has cardinality N. So when X is a finite subset of C and has cardinality N. So let's look at an example here. We can take our set C to have 3 elements. Then A is the natural numbers, which has 1, 2, 3, etc. in it. I'll draw that in a second. It's better to, let's do B first. So B is the power set of C, so we have the empty set, we have the set containing all of the single things, we have the sets containing all of the pairs, so the set excluding 1, the set that excludes 2, and the set that excludes 3, and then the set that excludes nothing. So that's everything in our power set of C, which is B. And then we can fill in a few things in our set A. So you have 1, 2, 3, 4, etc. And now we can map out this relation with a diagram. So the integer 1, that goes to every subset which has one thing in it, and there's 3 of those. And then 2 is going to go to everything with 2 elements in it, and there's 3 of those as well. And 3 goes to the 1 subset there with 3 elements. And nothing goes to the empty set because the empty set has 0 elements in it, and there's nothing coming out of any of the other natural numbers because those natural numbers would correspond to subsets with more than 3 elements, of which we don't have any in our set B here. So the most important example of a relation, which we're going to look at coming up in a future video, is the idea of a function from a set to another set. And so a function is going to be a relation because when you think about a function, it's a rule that takes an input in A and gives you an output in B, right? So the function is just described by certain pairs in AB, in A cross B. So all the information in a function is just contained by saying, is just contained in the set of pairs that tell you what the output in B is for a given input in A. And the function here, it's a relation which has to satisfy a special property, which you can think of as like the vertical line test from pre-calculus or algebra, which is that if you have x going to y, and so you can think about x is on like the horizontal axis and y being in the vertical, that y can be the only thing in the vertical direction in B that is assigned to be the output of the function from x, right? So if x, y, and xz are in this relation set that's defining our function, then y has to be equal to z because there has to be an unambiguous output from the function coming from the input x. And so that's the content of the vertical line test. And so in some sense you can think about like the graph of, so the function is kind of, this relation is kind of the graph of the function if you want to think about it that way. It's a set of, you map out the set of pairs for each x in A, kind of in the horizontal direction. You find the one in the vertical direction in B that's assigned to it. And then if you map out all those pairs of points, you get what you can think of as the graph. So that's the most important example of a relation between sets that we're going to look at.